Welcome back to video 5.3, the particle nature of light. So, to recap, Schrödinger and Heisenberg and de Broglie all took the development of the atom and were trying to explain why electrons behave the way that they do. And they said that electrons behave as waves when traveling through space. And that is true. But the wave model of light cannot explain all of light's characteristics. So then Albert Einstein, who was a really smart guy, proposed in 1905 that light has a dual nature. And so what that means is that it can behave as a wave when interacting with space or moving through space, and then as a particle when interacting with matter. So it can be a wave-like and it can be particle-like. Wave-like when traveling through space, and particle-like when interacting with matter. So when it's interacting with matter, what that means is that matter, remember, is anything that has mass and takes up space. So the photoelectric effect is what happens when electrons are emitted from a metal's surface when light of a certain frequency shines on it. So what helped Einstein come to this conclusion that light acts as it has a dual nature, it can act as a particle, is because when a metal gets really hot, we know that metal has electrons in it. And when light of specific frequencies, like sunlight, is shining on it, that metal will end up emitting electrons. And that is called the photoelectric effect. Photo because of light, electric because of electrons. So it depends on the frequency of that light. So when we're talking about the particle nature of light, we have to remember the quantum mechanical model. It all kind of comes back to each other. And we have hypothesized and have pretty much figured out that matter gains or loses energy in small specific amounts. These are called quantas. The best way I can put this into an analogy is to think of a quanta as kind of like an envelope. Okay, so there's only a specific amount of paper that can fit into an envelope, and the envelope's still closed. So matter is going to gain or lose energy, however much energy that can fit in that quanta. Okay, like what can fit in an envelope. And that quantum, okay, that is the minimum amount of energy that can be gained or lost by an atom. So if I'm going to hand you an envelope, that's the minimum amount of paper you can gain or lose. So whatever's in that envelope is the amount of energy that can be gained or lost. So that's what a quantum is. It's kind of like an envelope, or kind of like a packet. A photon is kind of like, I guess, in the analogy of with an envelope, it would be kind of like the stamp, in that it doesn't have any mass, but it carries the quantum. It's what gets that envelope passed through the mail system, is that stamp. So a photon is a particle of electromagnetic radiation, and it has no mass and it carries a quantum of energy. Another analogy would be a quantum being like a text message, and the radio waves and the airwaves that pass your text message through to each other, that would be like the photon. So a quantum is an amount of energy and it rides the photon. When we are doing our particle calculations, the calculation we're going to use this time is E equals H times V. Well, E stands for energy, H is Planck's constant, and V is still frequency from our last calculations for the wave nature of light. Planck's constant is another constant, and it is 6.626 times 10 to the negative 34th joules per second. You do need to know that value. 6.626 times 10 to the negative 34th. The way that I remember it is 6.626 is Lilo and Stitch, Stitch's aliens number, and then the Miracle on 34th Street is the exponent. So, we have two different equations now. We have the wave nature of light, which is the speed of light is equal to wavelength times frequency. We have the particle nature of light, which is energy is equal to Planck's constant times frequency. So whenever I read a question now, I have to decide which one am I using. So this example says, what is the energy of a photon from the violet portion of the sun's light if it has a frequency of 7.23 times 10 to the 14th inverted seconds? So what is the energy of a photon? So energy is what I'm looking for. I'm given frequency. Well, which one of those equations up there uses frequency? Well, both of them do. But which one is asking about energy? That would be the second one. So the equation I'm going to use right here is energy is equal to Planck's constant times frequency. Planck's constant is a constant that you have to know. It is 6.626 times 10 to the negative 34th joules times seconds. And in the question, it gives me the frequency of light for violet light is 7.230 times 10 to the 14th inverted seconds. So now what I can do is I can just take my calculator, multiply these two, and get the energy. So I'm going to do parentheses 6.626 times 10 to the negative 34th, close parentheses, because that is Planck's constant, times parentheses 7.23 times 10 to the 14th, close parentheses. And my energy value, the energy of that photon, is going to end up being 4.79 times 10 to the negative 19th. If your calculator gives you an E, that means that's the exponent. My seconds would have canceled out because that one was to the negative 1. And my unit for energy is going to be joules. So, take a second, make sure you can get that answer correctly. We're going to do one more practice problem. So, what is the energy of a photon of light with a wavelength of 434 meters? So the first thing that I'm going to do is, I know these are light calculations, so I'm going to write my two equations. Speed of light is wavelength times frequency, and energy is Planck's constant times frequency. So right here it says, what is the energy of a photon of light? So I'm looking for E with a wavelength of 434 meters. So I'm given wavelength. So I'm given wavelength, I'm looking for energy. So I go over and I look at my equations. And I've got wavelength in one equation and energy in another. But what do those two equations have in common? I hope you noticed frequency. So what I'm going to do first is I'm going to take this wavelength number and I'm going to plug it into its equation, which is the speed of light equation. So, speed of light is equal to wavelength times frequency. I know the speed of light is 3.00 times 10 to the 8th meters per second, because that is always a constant. Right here, I know that the wavelength is 434 meters, and I'm looking for frequency. So I'm going to divide for both of these by 434 meters. That cancels over on the right side. And when I plug this in, I'm going to end up getting my frequency as 691,244.24 hertz. So that's my frequency. So now what I'm going to do, that means that's a really fast moving wave, is I'm going to calculate energy. Because now I have frequency and I can figure out energy. Now, I only have to do this when it gives me wavelength and it asks me for energy. So what I'm going to do is I'm going to take my energy equation, which is Planck's constant times frequency. I'm going to take Planck's constant at 691,200. Oh, wait, no, that's not Planck's constant. That is, I'm going to scratch that out. So Planck's constant is 6.626 times 10 to the negative 34th joules times second. And then I'm going to plug in the velocity, the frequency number, which is 691,244.24 hertz. And when I plug that into my calculator, I'm going to get the energy of this photon as 4.58 times 10 to the negative 28 joules, because hertz is the same thing as negative seconds to the negative 1. So that is how you calculate the energy of a photon of light when you are given wavelength. So the main thing is from here on out, make sure you pay attention to what is given and what you're looking for, and choose the correct equation or combination of equations. Thanks so much for your attention.